Dear students, let's learn one more applications of the Gauss theorem, that is expression for electric field at a point due to an infinitely long uniformly charged thin sheet. In the previous derivation we had taken infinitely long uniformly charged thin straight wire. Now we are going to take thin sheet. Now what do you mean by exactly thin sheet? So the thin sheet looks like something like this. So this is a charged sheet. See, uniformly charged, infinitely long, very long, correct, charged sheet, and we want to find the field due to this sheet. Now, to find the expression, again we have to use Gauss theorem, and to apply the Gauss theorem, we always need a Gaussian surface, which is an imaginary surface that encloses the charge, and it can be of any shape. Now, the kind of the Gaussian surface which we are going to consider in this case is a cylinder passing through the sheet, so that one half is on one side of the sheet, the other half is on the other side of the sheet. Okay. So, to derive, let us consider the diagram. So, this is the infinitely long uniformly charged thin sheet of wire, and here we have a Gaussian surface, cylindrical, passing through the sheet, so that one half of the cylinder is on one side, the other half on this particular side. Okay. And we are going to consider 2 points on either side. One is a P on the right and Q on the left. So this is the face, one face of it. This is the other face. The next is the lateral face. So whenever we consider the Gaussian surface, certain amount of the charges are enclosed by the Gaussian surface, because the rest of the charges are here. So only through the cylinder, let delta Q be the small amount of the charge, and let delta S be the area here, delta S. If this is delta S, then the area vector will be like this. This is the area vector, and here the area vector will be like this, normal to the surface. What is the direction of the electric field? The direction of the electric field will be like this. This is E vector, perpendicular to the sheet. So this is the direction of the electric field here. So that the angle between area vector and the field is 0 degree, because they are along the same direction. Even here also it's 0 degree. Now how about the lateral surface? If you consider the lateral surface, the area vector will be perpendicular to it, like this, correct? If this is the lateral surface, then it will be like this in all directions, perpendicular, okay, perpendicular to the surface, like this. Then, so that what is the angle? Electric field will be along this direction. This is the area vector. So that the angle between the electric field and the area vector here is 90 degree. That is for whenever we measure the flux through the lateral surface. You know, this one, this is the flux. Okay. So there are 3 phases through which we have to measure the flux. One, end phase containing point Q. This is the end phase containing point P, and the other is the lateral surface. So what is the charge enclosed? That is delta Q, and delta Q by delta S will give you charge per unit area, which is nothing but the surface density of charge, which is sigma. So therefore the charge enclosed, delta Q, is equal to sigma into delta S. So this is the charge enclosed. So now let us find the flux through all the 3 surfaces. So therefore the total flux is given by the flux through the surface containing Q is E delta S cos 0 plus the flux through the lateral surface E delta S cos 90 plus the flux through the end face containing point P E delta S cos 0. So, this is E delta S cos 0 is 1, this is 0 plus again E delta S. So, that will be 2 E delta S. So, this is the total flux through all the three faces. Now, how to find the flux according to the Gauss theorem, which is equal to 1 by epsilon naught times the total charge enclosed by the closed surface. Total charge enclosed only, not on the entire sheet, which is delta Q. That is 1 by epsilon naught into delta Q from here is nothing but sigma into delta S. Sigma into delta S. So, that will give you again the flux through the entire Gaussian surface. Now, equating 1 and 2, we get 2E delta S is equal to 1 by epsilon naught sigma into delta S, The delta S will get cancelled. So, you will get E is equal to sigma by 2 epsilon naught. So, this is the expression for electric field due to infinitely long, uniformly charged thin sheet. And what you get to see here is E is independent of the distance, E is constant, okay, it is uniform, and E, it does not depend on the value of R means the distance. So, that is why using infinitely long, uniformly charged thin sheet, we can produce a uniform electric field on either direction perpendicular to the sheet, and it is directed outward if the charges are positive, it is directed inward if the charges are negative. The same expression you can even write in terms of the vector form. Vector E is equal to sigma by 2 epsilon naught. You can introduce a unit vector whose direction is same as that of the direction of electric field, and since the sigma is a constant, electric field is also constant. So, this is the one of the method by which one can produce uniform electric field by using uniformly charged infinitely long thin sheet of charge. Now, that completes chapter 1, and we are going to have a test soon. I am going to announce the date and the time. So, therefore, do prepare for the first chapter. The question paper will be posted in the group, and the maximum marks is 25 and the duration of the test is 1 hour. So, I will continue the remaining topic or remaining chapters in my next class. Okay, till then, take care.